If we're going to talk about load transfer systems, this is a little more low-tech than the previous presentation, but I think there's still some interesting messages here and some interesting trends to take note of. We talk about load transfer. What we're referring to is the ability of any transverse joint or longitudinal joint in a concrete pavement to move the load from one pavement slab to the adjacent slabs, thereby reducing the deflections in the slab. And if we reduce the deflections in the loaded slab, then we also reduce the rate of accumulation of fatigue, we reduce the stresses, we reduce the potential for pumping and faulting of the slab, and we may also restrain some of the curling and warping that has been mentioned in some of the previous presentations. A good place to start, of course, is the beginning, the earliest concrete pavements. We saw some references to the first German concrete pavement here in Poland. The records that I've searched indicate that the very first concrete pavement in the world was actually in Inverness, Scotland in 1865. Some sections nearby from 1872 are apparently still in service, but they were built so long ago I can find no photographs of them as they were being built, certainly, and I was not able to find current photographs. I tried to talk my wife into allowing me to go to Inverness to take pictures. She was afraid I'd spend my time on the golf course, so it didn't happen. The first concrete pavement in the United States was built in Bellefontaine, Ohio, and this is a photograph of that pavement section as it currently exists today, and some of that is the original 1865 construction. You can see the statue there of George Bartholomew. He is the engineer that designed and built that original pavement, and in the United States, if you build a concrete pavement that lasts 100 years, they put up a statue for you, so it's something for us all to aspire to. But these early pavements all had no dowel bars. They relied on aggregate interlock load transfer. They were all lightly loaded. They were designed for horses and carriages, relatively light loads. Very different situation from what we have here today. The first dowel bars in the United States, and I'll keep this very brief, I'm going to look at the United States only, but I assume that very similar evolution transpired in other nations across the world. But the first dowel bars in the United States were used on a roadway between two military camps near Newport News, Virginia. And if you believe the stories that are sometimes told, that you had Army officers that would travel back and forth between these two camps and the old original pavement that was first built before they rebuilt with concrete. The original pavement was very rough, and so you had officers driving back and forth across the pavement. They would spill their coffee on their uniforms. They were not very happy. And so when the pavement was to be reconstructed, these officers instructed the engineers that you will build a new pavement, it will last a long time, it will be smooth, and it will stay smooth, or you will be doing kitchen duty for the rest of your career in the Army. So the engineers said, okay, we have to design a smooth pavement, we're going to use concrete, and we're going to put dowel bars in that pavement, the very first dowel bars. We're going to put steel bars, 1.3 meters long, approximately 19 millimeters in diameter. And there was only one bar in each wheel path across the pavement. So optimized placement of dowel bars in the wheel paths, even at that early stage. This performed very well, and in fact led to very rapid then use of dowel bars throughout the entire country. By about 10 years later, half of the states in the United States were using dowel bars in their pavements. We didn't really know how to design them. There was not a lot of good theory for doing this at the time, so you can see that there were a lot of very different practices. Different numbers of bars, 2 bars, 4 bars, 8 bars, different diameters ranging from 13 millimeters to 19 millimeters, and different lengths of bars ranging from about 60 millimeters to twice that. So that, of course, led to a lot of research by a number of very famous people that are famous in the area of dowel bar research. Teller and Cashel, Bradbury, Freeberg, did a lot of research over the next 30 or 40 years, and their research led to recommendations in the American Concrete Institute journals in 1956, and those recommendations became essentially standard designs in the United States, and similar designs were adopted around the world. And these designs essentially ended up with dowel bar diameter being 1/8 the thickness of the concrete slab, and about a 30 centimeter spacing uniformly across the entire joint width, with sufficient length to make sure that the dowel bars were embedded in the concrete enough that they would have very little looseness, or very good load transfer, if you will. This is one of the studies that was done by Teller and Cashel in 1959, and you can see the looseness basically leveled out with a certain degree of embedment, usually between 6 and 8 diameters of the dowel bar of embedment. And so for this reason, and also for some others that I will talk about later, the standard length of dowel bars in the US anyway was established at being around 45 centimeters of length, with half on each side of the joint. And that would provide some allowance for the minimum embedment requirement plus the possible mislocation of the joint, misplacement of the basket, so you might have slightly more or less embedment on one side or the other. So clearly by now it was recognized that dowels were a very critical component of jointed concrete pavement, and perhaps the most critical part of the design of the joint itself. In addition to providing the load transfer that we've talked about, they were also to allow that transverse opening and closing of the joints to take place with a smooth dowel bar. And in order to provide service correctly, they had to last for the entire service life of the pavement. And for a long time, up until probably the 1980s at least, our standard design period was around 20 years. Now, of course, we're commonly designing pavements, concrete pavements anyway, for much longer periods now, maybe 35 years, 60 years in some places. California has talked about doing 100-year concrete pavement designs. So if the pavement's going to last 40 years, 60 years, 100 years, then the dowel bar needs to last that long as well. But in the 1970s, we were still using 20-year designs. In the 1950s, we were doing 20-year designs. By the 1970s, those pavements that we had built in the 1950s, many of those pavements, the concrete was actually lasting longer than the 20-year design life, but they were failing because of the corrosion of the dowel bars, because the original dowel bars provided no corrosion resistance. They were basically bare steel bars of the type that you see here on the left-hand side. And I do have to tell you that I just took that picture on a project earlier this year. So we still have some places that are not using any kind of corrosion protection. The middle photograph shows a picture of some dowel bars. These were only about 20 years old, 17 years old, I believe. And they had suffered a great deal of corrosion, particularly near the center of the bar where the joint is, and you have easy access for water and salts to enter the pavement, and that accelerates the corrosion. And what happens then if we have the corrosion of the bars, we can have obviously a loss of the section of the bar, so we have a loss of load transfer, a loss of restraint of curling and warping, and we can also have the corrosion that then prevents the joints from opening and closing. And if that happens, we would see this type of distress that you see on the right-hand side, where the joints become locked up, and as the joint tries to open during very cold periods of time, the joint simply fails along the ends of the dowel bars. So clearly a need for corrosion was indicated, corrosion protection was indicated, and that drove the first evolution that took place. Really, in the 1970s is when we started to use barrier-type systems of corrosion protection, with the most common being the green epoxy that you see here. I think that's also fairly common in many European countries. I think we used it a little thinner. Our layer thickness of the epoxy was only 0.2 to 0.3 millimeters of thickness. My understanding is that Germany and others use perhaps 2 to 3 times that thickness. But epoxy, plastic, coatings, paint, grease, the degree to which they would provide effective corrosion protection depended on the environment, how well coated the bars are, because as soon as you would have a gap in the coating, obviously you have a site then for corrosion to initiate, and it would then cause problems. So here we are today in the 1990s to the present, and corrosion is continuing to drive evolution. We need better corrosion protection systems, perhaps thicker layers of epoxy, as has been done here in some of the European countries, and also alternate systems. I think we've looked a lot more into different types of corrosion protection systems. Some of the newer barrier-type systems that we have, the purple epoxy, the non-bendable epoxy, I think has better adhesion to the bars. There's typically a cathodic disbondment requirement for this that is not present in the green epoxies. We have some much more sophisticated epoxy systems with multi-layers of epoxy. The outside of this bar is called an abrasion-resistant overcoat. And this is similar to the epoxies that would be used on underground pipe systems. And we're seeing this being used on some of the dowel bars in the United States. We have composite materials that are encasing steel core materials. So that's a composite dowel bar with a steel core and about 3 millimeters of epoxy coating around the outside. And then we also have used, in some cases, stainless steel cladding or stainless steel sleeves, which again provides a uniform, impenetrable barrier on the outside of the bars. We also have been using a number of non-corroding systems. We saw earlier in the last presentation some evidence of the use of composite GFRP, fiber-reinforced polymer bars. That is an area that's growing very rapidly right now in the United States. We've had a number of projects built, not so much lately with the cost of stainless steel, but there have been projects built using stainless steel dowel bars. 316L steel, very, very corrosion resistant, very, very expensive, but it has been used. A lesser grade of steel is the microcomposite alloys, which have very high chromium contents, probably similar to the metals that are used in many exhaust systems on cars these days, and the catalytic converter systems and so forth. So not quite as corrosion resistant as the stainless, but much less expensive as well. And the advantages, of course, that the metallic products have over the non-metallic products is that they have the same kinds of properties that we're accustomed to. So the design of the system is essentially the same as our conventional bars. We have also experimented with some passive cathodic systems where we're using a layer of zinc alloy of some sort on the outside of the bars, where the zinc will corrode preferentially and protect the underlying steel. Zinc alloy over steel, as you see here, this is about a 1 millimeter thick layer of zinc that's encapsulating a standard dowel bar. Galvanized dowel bars, which of course would have just a very, very thin layer, just a few microns thickness around the bar. And then we have some duplex systems where you have a layer of galvanizing on the outside of the bar and then epoxy over the top of that. So belt and suspenders, if you will. The epoxy protects the entire bar, but if there's a slight gap or a defect in the epoxy, you still have the galvanizing there to protect the steel, so there's no corrosion. At the same time as we've been looking at these different types of protection systems, we've also been looking at the different structural sections, attempting to make the structural sections more efficient. And in fact, this last bar on the right-hand side is a tubular bar. It's a hollow bar. It has a wall thickness of about 3 millimeters thickness. The diameter is slightly larger, so you have a very similar stiffness to that of a solid bar by having a larger bar, and you have a larger bearing area, so your bearing stresses are a bit lower. This is simply following the same sort of evolution we've had with buildings. You would not build a tall building using large steel blocks. No, we use I-beams and wide flange sections. And the thinking with these tubular bars is the same thing. We don't have to use a solid bar. We can use a tubular bar and put the steel or the material that is being used where it does the most good, because there's very little bending capacity to the center portion of that bar. And we have plenty of shear capacity in any case with typical dowel loads. So if we do this, if we use these tubular sections, this results with substantial material savings, which contributes to sustainability. Reduced weight of the bars. You can put many, many more bars on any given truck or boat or whatever, so your cost of transport per unit is much lower greenhouse gas emissions per unit. And then the overall economics depends on the market, because you have less material, but there is more fabrication involved in using tubes. You have to bend a piece of strip steel into a tube and weld it and grind the weld off. So sometimes it's less expensive, sometimes it's more. It's about the same in terms of the cost very often. So that's one way of optimizing dowel shapes. There have been others that have been looked at. In addition to the tubes, we have a number of plate steel manufacturers. To date, most of the plate steel dowel bars have been used primarily on interior floor slabs, thin slabs, and so forth. They obviously offer the advantage of having a much larger bearing surface, so less potential for faulting and so forth. They are a little more difficult in terms of the coating of the bars. To achieve a corrosion-resistant coating. Again, if you're in an interior application, that's less of a concern than in exterior applications. But we do have some of these in exterior applications as well, and there have been some coating systems successfully applied to them. There's also been a bit of research done to elliptical dowel bars, which again are trying to optimize the shape of the bar to provide more bearing surface area, to lower the contact stress between the dowel bar itself and the underlying concrete, which then reduces the potential for joint faulting and step off across the joints. The last thing we can do is we can look at the length of the dowel bars. I think historically we have over-designed the length of our dowel bars. And we're starting to see some people looking at this, a return to dowel mechanics, if you will. In 1925, Timoshenko and Lessels developed this equation for predicting the deflection of the dowel bar within the concrete, assuming a semi-infinite bar embedded in an elastic solid. Okay, and the term Y is the deflection of the bar. And if you look at the deflection of the bar and you recognize that the steel, if you model the concrete as an elastic solid, then the bearing pressure is directly proportional to the deflection of the bar. Bengt-Freberg in 1938 determined that if we cut the bar at the second point of contraflexure here, and had at least that length of bar embedded in the concrete, then Timoshenko's model would be accurate to within about 3% on our bearing pressure. And so this was the bearing pressure model that Bengt-Freberg developed with that in mind. So it was never really about how much bearing pressure we need to have or need to limit it to, but it was about selecting a length that basically validated the original model with a semi-infinite embedded length. Of course, we have much more sophisticated models now. We can very easily evaluate the bearing pressures under different length bars. For example, these are some graphs that were produced by Dr. Kuzanovic, who's in the audience here today. And these are 25 millimeter dowel bars, 22 centimeters of embedment in the top, 12.5 centimeters in the bottom. And you see that there's only about an 11% increase in the bearing pressure when we cut that bar almost in half. So there's a significant potential then for savings by using shorter bars, as long as the bearing pressures, the increased bearing pressures, which we can model and calculate, are not excessive. And we have actually seen in a number of states are using shorter bars now in certain applications. The state of Minnesota has for a long time used bars that are about 7.5 centimeters shorter than standard. And we're seeing even shorter bars being used in repairs. We can also look at improving the layout of the dowel bars. Rather than using uniform spacing of bars every 30 centimeters or every 12 inches, this is in English units here, I apologize, but we can optimize the placement of the bars, focusing on placement in the wheel paths, just as those first military roads back in 1917. And then we can evaluate the behavior of those. We very commonly see this sort of thing. Here we have 5 bars per wheel path. This is on the Illinois Tollway around Chicago. They've eliminated a few bars. That's a few less bars, a little less steel, a little less cost, a little less greenhouse gas emission, conservation of raw materials, right? The state of Utah, their new standard is 4 bars per wheel path. On some lower volume roads, we're seeing 3 bars per wheel path. And if you have a low volume road with traffic in opposite directions, sometimes we're only seeing 1 set of bars only in the outside wheel path and no bars at the inside wheel path. And this particular road has been in service for 20 years or more now and is performing very well with only 1 set of bars in the outside path. And it does see heavy truck traffic from farm equipment and so forth, and transport of grains. So there are many things that we can do to optimize and improve our dowel system design. The dowels are only one component of the concrete pavement, and we are concerned with trying to be green in all things. But there certainly has been historically a lot of resistance in the past to using these newer systems. And the excuses that are given are that it's not in the current specifications, so we can't use that. The other excuse is, well, we haven't had any experience with this. So build us a test section and come back in 20 years and then we'll consider doing it then. Or we don't have a good, quick way to evaluate the potential performance of these. It's not fast enough. Or there's just not enough motivation for change. I think in many highway agencies, there is no reward for doing new things, and there's only a potential risk of having a bad experience. There's no reward for having a good experience. Some of these things we can address, and I think we have addressed. We have tools now, such as the DowelCAD software, which will easily calculate differences in bearing stresses for alternate dowel systems. This is free software that is available on the American Concrete Pavement Association's technical website. And of course, we have finite element analysis, as we've talked about previously, which allows us to evaluate alternate dowel bar systems, alternate sizes, different materials, different spacings, and can tell us when the systems that we have designed are going to be adequate or not. It can give us a good indication of that. We also have a new load deflection test, which I will talk about on Wednesday, so I won't go into it here. But rather than testing individual dowels for their system, for their mechanical properties, we can test entire systems of dowel bars across a large section of pavement and evaluate the deflections across those pavements. So again, I'll talk more about that Wednesday rather than now. I think that sustainability is a motivator now. We don't need necessarily top-down direction. Everyone is interested in sustainability now. The greenhouse gases that are involved in the manufacture and transport are going to drive us to less energy-intensive types of systems. The longer potential service life of these systems, their recyclability, as we've always had, the economics that are associated with optimized sections and reduced lengths, and we are starting to see the development now of environmental product declarations that talk about the environmental impact of individual products for our pavements. Right now we're working mainly with cements, but I know that some of the dowel manufacturers are working on developing EPDs for their products as well to help to identify which are the most sustainable. New technology also motivates implementation. As we're starting to see more use of charging systems in pavement, embedded charging systems for inductive charging of vehicles as they are parked or moving along the roadways, or even instrumented roadways where we're sensing the pavements. We can't have other metals in the pavement system that would interfere with the inductance process or interfere with the sensing systems. So that's moving us into things like the FRP dowel bars or stainless bars, something that's non-magnetic. So these are things that are helping to motivate implementation as well. We also have recently noted a type of a pavement distress that perhaps suggests that with our accelerated paving systems, our dowel bar systems are too stiff for the young pavements, and we're seeing some delamination distresses across the dowel plane in the pavements. And this has driven at least one of our agencies to say, okay, we need to have smaller bars and more flexible bars. I think this type of thing will move people into tubular systems and FRP systems in the long term. So the future, I think, if we look at the future, if I get my crystal ball out and look at the future evolution, I think what we're looking at is sustainability continuing to drive the innovation and the implementation of these newer systems because of the advantages that I already mentioned previously. And I think what I'd like to see, and has not happened yet, would be catalogs of dowel system design. For a long time, the design of dowel bars was treated as kind of a standard. Okay, everyone used the same length bars, the same sizes, maybe one size difference for larger pavements and one size difference for thinner pavements. We need to really be designing our load transfer systems and evaluating their total capability and have a catalog that says, all right, if you're going to use FRP bars, this is the sizing and spacing. If you're going to use tubular bars, this is the sizing and spacing. Solid bars, this size and spacing. So design based on what we actually need for any given project, recognizing that different levels of traffic, different weights of traffic, different climates, different foundation stiffnesses, all affect the amount of load going into the dowel bar, and the dowel bar system should be designed accordingly. So, wrapping things up, the evolution of load transfer systems, we've had more than a century of improvements now in the design and construction and material selection for these systems, and I think that going forward, the journey will continue to take place and evolve. So I thank you very much for your time and attention here today. Look forward to talking to you later.